Okay, let's talk about our introduction to spread spectrum. First of all, let's talk about what is spread spectrum. There's two major kinds of spread spectrum in use today, not to be construed as the only two methods of doing spread spectrum. But these two are pretty much washed up to the top as being the two that most want to implement, and that's direct sequence spread spectrum and frequency hopping spread spectrum. Let's touch a little bit on the history of spread spectrum, a little bit of history of the amateur spread spectrum, and who in the amateur communities, and of course who in the commercial community are using spread spectrum today. What are our possibilities? Why are we doing this? You know, it's spread spectrum. Let's do it just because it's spread spectrum. Actually, there's quite a bit that we can gain from it. And those of you that attended the PRUG session last night, you can see a lot of the advantages. In fact, they have it implemented, and you could see the speeds that they were able to transmit digital images. And that's all an inherent property of spread spectrum. Talk a little bit about PanSat, which is a spread spectrum amateur satellite that I'll touch on a little bit more, and of course touch on what are the hardware issues, what are our present FCC Part 97 rules that govern our spread spectrum usage, and what are our future plans in the amateur spread spectrum. And then, as I said, we'll entertain questions at the end of it, but if you have questions during the talk, please feel free to raise your hand. Okay, there will be a quiz at the end. Okay, a good instructor comes up, stomps his feet. This will be on the test, right? What is the definition of spread spectrum? And this is coming out of the Peterson, Zimmer, Borth textbook on Introduction to Spread Spectrum printed by Prentice Hall. And they have spread spectrum modulation refers to any modulation scheme that produces a spectrum for the transmitted signal much wider than the bandwidth of the information being transmitted independently from the information-bearing signal. Key word here, independently. All right, let me pick out the key words. We're going to transmit data. We're going to transmit a data stream at a certain bit per rate sequence. However, as we know, let's take 9600 baud. We got 9600 baud and we're going to use it on 2 meters. We know that's going to take up a narrow bandwidth of about 20 kilohertz. All right, that's within the definition of Part 97 rules that allows us to be able to do that. And we know that if we increase the bits per second rate, then the bandwidth widens. Now we're outside of what we're allowed to do on 2 meters. In the case of spread spectrum, what we're going to do is we're going to take that data rate and we're going to introduce a spreading signal into it and then make this signal even much wider than what the information-bearing signal needs in a narrowband sense. So the transmitted signal is much wider than the bandwidth of the information. So we got to introduce a separate code in order to get our information spreaded, and that information code is separate from the spreading code. Let's start off with something that we're familiar with. Let's talk about a narrowband system. We know in narrowband communications that we have a message that we want to send. Now this message can be either digital or analog. Then we come in here and then we mix it with an intermediate frequency so that we can basically step it up into the RF range and then be able to transmit it out. And then we're very familiar, if we were to take a look at this on an oscilloscope or a spectrum analyzer, we see that all of that information is put in a very narrow portion of the frequency spectrum, thus the name narrowband communications. Now, this of course comes across the ether in the atmosphere, and then comes across on the other side somewhat attenuated, a little bit of noise added to it. Then we demodulate it, and then we have our message come back out. Well, a spread spectrum radio uses the same components as a narrowband radio and introduces a new block in our block diagram. In this case, we saw that in a narrowband system, we had the message comes into a carrier oscillator. Here's our narrowband waveform. Everything we see from here over is familiar. We understand this part of it. Well, here's what we're doing. We take a pseudo-random number generator, or PN generator. This is a pseudo-random code, and it's a digital code, square wave. We run that into a doubly balanced mixer with our information, and then what comes out is this information spread out over several tens or several megahertz of frequency. This gets transmitted. Of course, the attenuation will be down, a little bit of narrowband noise added to it, pulse noise. Comes in, we take that same code sequence, run it through the mixer again, then what pops out is that narrowband signal. Then we run it through a demodulator and we got our message. That's it, gentlemen. That's how it's done. Now, one of the inherent capabilities of spread spectrum is its immunity to noise. Well, most noise is narrowband in nature or pulse in nature. If that is added to a spreaded signal, by virtue of despreading, the act of despreading here, those pulses basically go away. So that is why you can have noise immunity. The other one is immunity from multipath, because again, from the despreading, you take those multipath signals, they don't correlate, and they're rejected. Now, where the magic comes in is, of course, these pseudo-random generators. And there's entire mathematic books devoted to nothing but pseudo-random generators. So this block diagram right here, we could spend lectures on end just on those alone. But suffice to say that this is a code sequence that looks random. If you were to look at it on an oscilloscope, you would say, gee, that looks like noise. However, it's pseudo-random, meaning it is like noise, but it has a sequence, and it's a repeatable sequence. So that's why it's a science unto itself, because how can we make something look noise-like but yet be repeatable and deterministic? Because noise, by definition, is not deterministic. But we can't just inject noise in here because we wouldn't be able to demodulate it. We can't just inject noise at both ends. So properties like these spreading codes being very short, okay, or very long, determine whether or not we can correlate it in a very quick amount of time or a very long amount of time. Also, the speed at which this code, what is called the chipping rate, determines how much the signal is spread. Now, what I've just described to you here is what's called a direct sequence spread spectrum signal. And if you were to take a look at that on a spectrum analyzer, this is what it looks like. You have a main lobe where the majority of the energy is contained in many side lobes. And of course, it tapers off for the amount of energy that's actually there. But you would spread your signal on a center frequency, and then determined of the chipping rate and the spreading code determines how wide you're going to spread the signal. So in the case of the Prug people that gave their presentation last night, they were limited in bandwidth. So how do they tweak that down? Do they just tweak the RF part of it down? No. They actually tweak the chipping rate down. And then that brings in the actual band limits that they were allowed to. That's why their system, they said, was capable of 2 megabits. But because they were band limited and they had to crank down on the chipping rate, now they were down to 800 kilobits. Starting to make sense? Okay, now you want to go back and watch their lectures again. Now, direct sequence spread spectrum is probably a little harder to intuitively understand. And that's why I use the narrow band, because all of us understand that, and we can take one step further and understand direct sequence. Frequency hopping, on the other hand, is really quite simple, and it is described pretty much as the name implies. It frequency hops. And what we do here is this is a narrowband signal that hops around. And it hops around at the rate determined by the pseudo-random sequence. So you don't know where it's going to hop to next. You have to look at the code sequence to figure out which hop cell it's going to be into. Then you determine how long am I going to transmit on that frequency. That's called dwell time. And that's on the order of milliseconds. And of course, that's limited by the circuitry we can buy today. If you were to do this in a synthesized fashion, how long does it take for a PLL circuit to lock up? Okay? Now, if you get a chance to listen to Tom McDermott's talk about the TAPR frequency hopping spread spectrum radio, he'll describe how they're using two oscillators, one that's locked on and transmitting, the other one that's being commanded for the next hop so that it can settle down and switch over and use it and then go back to the other one. So that helps speed up the hopping sequence and also get you faster dwell times. The bandwidth of a frequency hopper, well, you just determine what your bands are, determine how many cells that you want to have, what your coding sequence is, and then there you go. This typically is the easier one to implement, and this is the one that you see the military using and many of the commercial spread spectrum radios using. Because that's kind of one of the questions when you look at a spread spectrum product, is it frequency hopping or is it direct sequence? And there's, just like they talked about last night at the PRUG meeting, which one's better? Well, which is your best baseball player? You know, that jury is not out as to which one is better. Okay, there's a lot of arguments. And you can spend days and days and days arguing with each other, the ones that like direct sequence and the ones like frequency hopping, right? Right. Mm-hmm. And I don't want to even get into those arguments. What are some of the advantages of spread spectrum? And I think they kind of stole my slides last night because we had the same bullets. One of the advantages of spread spectrum is what we call overlay. And this is something that is kind of optimistic. In other words, you've already got a service using an available bandwidth, and these are narrow band users. And what you want to do is you want to introduce a spread spectrum radio into it such that you both share the same spectrum. And you, the spread spectrum user, by the inherent nature that spread spectrum can tolerate narrowband users because of the despreading action, you can basically share that spectrum. Okay? Again, the jury's not out on that. There's a lot of bar arguments over that one. Okay? But theoretically, you should be able to do it. Now, that would probably have to look at that in a controlled situation. If you were to regulate it and say, okay, we're all going to agree upon this, you could probably make it work. But you know how much chaos there is in ham radio. Immunity from interference, otherwise known as anti-jamming. If you were to sit and read an old piece of literature on spread spectrum, they'll tell you about the anti-jamming properties of spread spectrum, you know. And so, you know, you just get this militaristic sense of spread spectrum, you know, anti-jam, I can get in there and you can't jam me. Well, the truth of the matter is, if you were to take a narrowband signal and just pump up the power and just go out there and try to deny the use of that frequency, spread spectrum is going to laugh at you. However, if you take a broadband signal and just broadcast that out there, yeah, you can disrupt spread spectrum. Spectral efficiency relates to the capacity of users. Now let's take that direct sequence signal and we have the spreading code. Well, now how do you say, how can we have conversations on here? Well, person A and B can talk to each other using code 1. And then person C and D can talk to each other using code 2. So what would we imagine a ham radio, spread spectrum ham radio, the future looks like? It's not going to have a frequency dial on it because it's going to have, it's already at spreading frequency on a center frequency. And God forbid it's going to look like a CB radio. It's going to have channels on it, which is to say that those are spreading sequences that they're choosing. So now, here's the fun part. You find these spreading sequences that don't interfere with each other. Let's take frequency hopping. If I'm hopping here and somebody else is hopping over here, then we're not going to interfere with each other. Occasionally, we might land on the same frequency. But since we're using forward error correction, we can recover from that error. But that's only going to happen every once in a while. That's what's known as codes that are orthogonal. And a researcher by the name of Gold did a great deal of research on all these codes to find out which ones were best, and they were the most orthogonal codes, and these are known as the Gold codes. There's another famous researcher out there of pseudorandom sequences named Barker. Those are known as Barker codes. So you'll probably hear those names when you start studying up on spread spectrum. Multiple access capability. Well, I pretty much, cost. I ran over cost. Theoretically, the cost of this radio would be less than a narrowband radio. Now, of course, that's not realized today because we don't have those parts up to a consumer level. Multiple access capability.
Why do you say that? Why theoretically it's less?
Because the component count is much less on a spread spectrum radio. Yeah, I know it's hard to relate because you've got to have something to take a look at that right now.
Because it's more digital.
Yes. Well, it's a digital component. You don't have as much RF components, except, of course, to get it from the IF on out. But then you don't have to deal with VFOs, for example, so on and so forth. And again, it's another theoretical. This is essentially what should happen.
You still have to apply the standard narrowband IF filtering techniques or not?
Only on the, not to the greater extent where you have to have so many stages.
Generally don't need power.
That's another issue too. You don't need the power. How many spread spectrum radios you know that's over a watt? How many do you even know that are even 1 watt? Okay, the Prug radio is 30 milliwatts. Okay? All right. The multiple access capability. All right. When we grew up with ham radio, we learned about frequency division multiplexing, FDMA. What does that mean? You choose one frequency, I choose another. We don't interfere with each other. Then we learned how telephone did it. Telephone does it by time domain multiplexing. They basically use the line for a short period of time for you, and then use the line for a short period of time for me, and then we just time multiplex. Well, this is the third dimension. Code division multiplexing, and I've already explained it to you. Use different codes, and you can use the same frequency. Because we're each hopping at different codes and we don't land on top of each other, then we don't interfere with each other. Multipath rejection. I explained that because that signal coming in has to correlate. And if you have a multipath signal bouncing off a building or off a mountain and coming back and it doesn't correlate, it's going to be rejected. Signal capture, much like an FM radio has a signal capture capability, spread spectrum has that inherent capability. Processing gain is actually by virtue of spreading the signal out, using the chipping rate, you realize a processing gain just from the mathematics of it, not so much from the signal-to-noise ratio part of it. you don't even measure spread spectrum in signal to noise ratio. You measure it in bit per noise ratio, or what you see as ebb null, energy per bit per noise, okay, what's called ebb null. And then precise ranging, see, actually, the beginnings of spread spectrum go back to the early days of research of radar. They wanted to be able to have finer resolution on radar, and what they learned is by using a random sequence, a pseudo-random sequence, they could be able to get that precision. So from the early days of radar began the beginnings of spread spectrum. Yes?
Multipath rejection, what do you really mean? And the reason I ask that question is I use spread spectrum radios on buoys, and I get multipath rejection when my receiving antenna is low. Also, the GPS does have multipath problems when they go to certain antennas. So what do you mean by multipath rejection in spread spectrum?
Okay, the question is, what do I mean by multipath rejection and spread spectrum? Okay, first of all, what is multipath? What is the multipath problem? You got two signals coming into the receiver, right? Well, these two spread spectrum signals coming in, that you've got one that's coming direct and another one that's coming via a bounced method, okay? There is going to be an amount of delay associated to that. Understand that this signal was created by this generator mixed with the data. Now, if we were to tie these two generators together, there's some finite amount of delay between the transmitter and the receiver. Okay, so this code generator technically would have to be lagging this one by some finite amount. Now, if that's if the signal being transmitted is a direct transmission, okay, and the bounced one's going to have that finite delay plus some more. This generator, when it correlates and locks on to the direct signal, it's going to stay with it because that's the one it's locked onto, it's found it, it's happy with it, and you've got your big correlation signal and you've made a lock on it. Now this reflected signal, it's a weaker signal and it's a delayed signal, it's not going to take a lock on it because it's already locked on the other one. And even if it did lock on the multipath signal, heck, if it's a good signal, it's nice and strong and it's not wavering, heck, it's happy with it. It locks onto it and keeps it and rejects the direct one.
Are you saying there's no multipath?
There is multipath problems, but it's much reduced from narrowband.
No, I feel when my signals get clobbered, they're clobbered.
Are they being clobbered from multipath?
Yeah.
Okay. Then I'll have to talk afterwards, but I need to move on here.
I just want to say that it's multipath. That's the problem.
This is an introduction. You're taking it a little too bit further here for that. I'm saying it has immunity to multipath. I didn't say it was immune from. Okay, let's talk about some disadvantages because it can't all be that good, right? All right, some of these are disadvantages, and actually they're not so much that they're disadvantages from a technology point of view, but they're disadvantages in a perception point of view because we have a certain paradigm that we're working in what we consider communications. So spread spectrum brings on a whole new way of thinking, so you kind of have to clear your mind and think out of the box. It has privacy. Well, that's actually kind of a good thing because not that it has privacy in the fact that you can't get into it and listen to it. It's just that if you're not actively, consciously trying to listen to that signal, you're not going to hear it. So you have some sense of privacy using a spread spectrum signal. And that's an inherent property, and it also has a couple of other names associated with it. You'll see the LPI, or the low probability of intercept, or the LPR, low probability of recognition. which is probably a better definition here. But you see, in the old days when spread spectrum started up in the military, the enemy didn't know what it was, and they didn't know what they were looking for. They thought they were looking for a narrowband signal, and that was a good thing, because you didn't want them to know what to look for. If you know what to look for, you're going to find it. Give enough time, you're going to find it. But if you don't know what you're looking for, and you're looking for an old method, then that's where you get your privacy or your LPI or your LPR. Another issue that keeps being brought up, we're raising the noise floor. Understand this signal is spreading, and it's spreading out over a wide bandwidth. It's not like a narrowband signal where it puts all of its energy in a very narrow bandwidth. It's putting all of its energy in a very wide bandwidth. But of course, if you look at it on a spectrum analyzer, it's much lower. So now you kind of see on a spectrum analyzer this noise, what we call the noise floor, and everybody's saying, oh, this is additive. Every time you add a spread spectrum transmitter, now you raise that noise floor up a little bit more. And again, this is another one of those bar fights. The last one here, corruption of incumbent users, particularly weak signal and repeaters. This is where the weak signal users are really after the spread spectrum people by saying, look, you're clobbering my noise floor. Now I can't do my weak signal communications. And also the repeater users saying, no, we're not going to allow spread spectrum on the repeater frequencies, because now you're going to, every once in a while, let's say take a frequency hopping radio, lands on a repeater input, and it keys up the repeater. However, they don't realize that that dwell time is in the order of milliseconds, and many repeaters have Kerchunk filters on them. They'll never even key up.
Question, isn't that raising the noise floor only an issue for corruption of incumbent users? If these codes are really orthogonal, who cares from the spread spectrum point of view?
Well, from the spread spectrum point of view, there's also another argument of how many spread spectrum users can use that frequency, because there's only a finite number of orthogonal codes, okay? Because after a while, then we're going to start reusing those codes, or we're going to start using codes that are not as orthogonal. There's a number of orthogonal codes that are really orthogonal, but there's only like a couple of dozen of those. And then you've got codes that are kind of, orthogonal. And then you got codes that you don't even want to use, okay? So there's been a lot of argument about what is the theoretical user limit, okay, after even if you had an unlimited number of orthogonal codes. And even the jury's not out on that one either, because there's I've seen a lot of formulas and a lot of theory put into that, but it's not been put into practice just yet. Now, a part of the other problem is even like the plug users, and we here in our spread spectrum communications, like we've been doing spread spectrum on 900 megahertz. Well, who else uses 900 megahertz? Paging systems, right? So what we found is when we did our experiments, guess what part of the day we couldn't communicate? The busy hours. And naturally, midnight's going to be the best time to communicate, because people aren't paging each other, okay? And then 2.4 gigahertz, who uses that? Microwave ovens. So they couldn't communicate in the morning and the evening. I think people are eating around that time. It's things like that that are, because the frequencies we're allowed to use spread spectrum in are ISM bands. So you have to be careful about why you can't communicate. Is it because I've got too many users, or am I hitting that theoretical limit, or am I competing against something else? ISM stands for Industrial, Scientific, and Medical. And these are the so-called garbage bands that the FCC set aside, allowing certain equipments to emit unintentionally these frequencies. Okay? These are not intentional. These are not transmitters with antennas. These are pieces of equipment that by virtue of their operating emit frequencies. Well, they allow them to emit them in these bands for industrial, scientific, and medical purposes. Kind of the same reason why you don't want to go into a hospital and it says no use of cell phones. The reason why is because you're interfering with the medical equipment, with a transmission in that frequency band. But they already know that they're not interfering in the bands that they're allowed to, so to speak. Yes, sir.
If you have a lot of users in a small area, are you going to get an additive effect from the medical a lot?
Oh, is it going to be a linear additive or a logarithmic?
Yeah, I mean, are you going to see like 10 people on there, and like say within a small town, and there's 10 or 15 packet lengths running on 900 megahertz?
Uh-huh.
Are you going to, or analog-wise, did you see an additive effect?
So the thing of it is, the first couple of signals are going to be below the noise floor. You're not going to even perceive them. And then they say, and this is the mathematics that I see, they say it's additive. For every person you add, it raises it. And this is the mathematics. But to me, that doesn't make intuitive, or I should say, extemporal sense, because I've seen, as you add devices, it's more of a, like you adding decibels, you know. Unless you have a power increase, you're never really going to see a change on it. Again, that's another one that we've not had an opportunity to put, like you say, 10 or a dozen users up there and actually put the spectrum analyzer and view this ourselves. Because every time we do this, do our spread spectrum communications, I mean, we can only get about 3 or 4 of us.
I've heard the question come up about this because you have some kind of propagation, particular propagation within such that then on HF, you have a problem with you have so many people on at the same time spreading all the way across that it would be unusable.
Yeah, that you're right. That's one of those bar arguments, but it hasn't been borne out in experimental in an experimental fashion. So I can't answer your question. All I can tell you is what the numbers say. The numbers say what you just described. They say it's additive and it's going to be destructive. And then that's been what a lot of the naysayers have really latched onto, saying spread spectrum is so destructive we don't need it. But the thing of it is, we've never actually put those systems on the air and proven those numbers. Does that help? You still look confused.
Well, when you say destructive, you mean destructive to analog? Is that what
well, in the sense of amateur radio, it's destructive to the incumbent users, okay? Because we go out there and say we go to a frequency coordinator. We say, well, we want to do spread spectrum and we're going to use 2 megahertz. Well, he looks at his constituency and sees how many repeaters, weak signal, and all that, and he says not only no, hell no. Because he doesn't know what the results are going to be. And despite us trying to show the numbers or saying, look, we want to experiment, let us find out, they go back to the numbers and then try to prove us wrong. Since we're an experimental service, I say let's get them on the air and prove it. And let's get the measurements and show it instead of us arguing over what the numbers say. But if you are a regulated service, then that's a much different animal, because then you have a carefully controlled environment. You can do whatever you want there. Does that make sense? Okay, right back here.
You mentioned that it's basically the signals that appear below the noise floor, but you're putting out the 1 watt at a particular frequency and then you're hopping over here. Wouldn't you see that spectrum series of spikes if you look at the spectrum analyzer on the band?
Well, it depends upon your distance from the transmitter. Because then one of the things that I haven't mentioned is what's called the near-far effect. If you're, let's say you're a spread spectrum receiver and you have a very powerful narrowband transmitter very, very close to you, you're just going to clobber them. It's the same desense problem that you see whenever you get 2 narrowband transmitters together. Okay? And at the same time, if you're very close to a narrowband transmitter, you're going to see more of his energy just by virtue of being closer. but the further away you get from them, you're not going to see their spectra. So now, if I'm going to sit there and say, okay, I live in Chicago, and we have 24 spread spectrum transmitters, and now I'm going to put up a spectrum analyzer. Well, you've got to pay attention to how far away are you from everybody to judge that raising. Okay, right over here.
In practice, how long does it take for a receiver to lock on?
That depends upon the spreading code. If you have a very short spreading code, it's going to lock on very quick. But the disadvantage there is that you may have false correlations. So how do you deal with false correlations? You make the code longer. What's the disadvantage? Now your lock-on time is longer.
Can you tell us, in practice, with stuff that people are actually using, how much time?
Oh, it's in the order of milliseconds. And take for example the CDMA that Qualcomm uses. Okay, they use spread spectrum with their CDMA system. And what they did is they used 2 codes. In fact, GPS uses 2 codes. Does everybody realize GPS is spread spectrum? A lot of people don't know that. So take a look at your spread spectrum receiver that you all own, and take a look at that little tiny antenna and look how far away those transmitters are. This will give you some idea of some of the capabilities spread spectrum can give you. Now, both Qualcomm and the GPS system use 2 codes. They use a short code, and that's what we use. That's the coarse acquisition code that we use on civil frequencies. And that allows a very quick acquisition. Boom, there we are. Disadvantage, we have less accuracy when we use our GPS receivers. Now, on the military side, they have 2 frequencies. The coarse acquisition code sent on 1.5, and then the P code sent on 1.2. Well, that P code, get this code doesn't repeat itself for weeks. Okay? This is a very, very long code, and thus they get their accuracy by using this much longer code. But how do you know where you are in this very long code? Use the coarse acquisition code to give you a hint of where you are in that long code. And that describes GPS, and that also describes, almost in a nutshell, you can infer how Qualcomm does it. They use a short code to be able to do these linkings to do setups and teardowns, and then once you're there, they give you the long code, and that's where you're actually talking on. Yes, sir?
You mentioned using 1 watt or less. There's also, I don't know what the status of it is, there's a request to raise power levels. What does this do to the noise? Power levels on spread spectrum units. What does this affect on the noise floor?
Well, it's obviously going to affect it. Now, the thing of it is, you want to answer quantitatively what it's going to do. We don't know until we actually put it in practice and actually measure it. And then,
as long as you have few users, you probably don't really have a perceived.
That's true. And again, that gets back to a regulated service. You can sit there and say, look, we're going to transmit at this power, but we're going to, due to the effects it gives, we're going to limit it to 2 or 3 receivers transmitters. And you can control that. But understand what ham radio is like. Ham radio is more like the military. Think about it. John Costas wrote about this in 1959. He used amateur radio to describe the chaos that is very much like in the military system. Military, you're both trying to communicate and deny each other communicating. Hey, we do the same thing. We deny each other ability to communicate, right? But it's kind of like that, but there's so much chaos, there's no regulation, we just pop on a frequency, any mode, and we have gentlemen's agreements that say, okay, RTTY here, CW here, phone here, right? So that we don't kill each other. And now, how do you introduce spread spectrum into all of this? Especially on the HF frequencies, hard to do. A little bit easier on the much higher frequencies because we're not really doing anything up there. Okay? What's some of the history of spread spectrum? It goes all the way back to the 1920s with the advent of radar, and it was idea to enhance resolution of the radar ping coming back. In World War II, the military used it to combat jamming. It was in World War II, a lot of famous scientists got together up in the Cambridge area at Lincoln Labs and was trying to figure out a way to stop the enemy from jamming. And they were looking at it from the point of view of how can I stop this jamming, when really they all of a sudden changed their thinking and said, well, we don't stop them doing the jamming. What we do is we make a better system that's immune to jamming, and that's where spread spectrum came out of it. The history, if you want to read about the history of spread spectrum, fascinating history. Fascinating to follow the thinking of the scientists at the time and how they came up and discovered it. Today, spread spectrum, old hat, okay? But imagine what it was back in the 50s when they were trying to figure this animal out. In 1959, John Costas, a very famous ham, K2EN, the Costas loop. Everybody knows the Costas loop. Everybody's built one, right? Right? Okay. He wrote a paper called Poisson, Shannon, and the Radio Amateur. And this is the paper he described, he likened amateur radio to the military. This is the paper that John Costas, a ham, first introduced the concept of using spread spectrum on amateur radio. It was published in the IEE, and you should be able to find that. Pardon?
IRE.
No, IEE. No, it's IEE. I've got the paper. It says it right at the bottom. First published in the IEE in 1959. The paper is, okay, TAPR has a spread spectrum book that's being printed right now. And this paper is in that book. Okay? It's reproduced in a lot of other IEEE publications too. 1970, when the global positioning system was being conceptually designed, it was in 1970 that they chose to use spread spectrum. Now think about that. That's 28 years ago. Think of how profound a decision that was back then to take a very, perhaps not as well known in the engineering sense, modulation scheme and literally say we are going to use this for our forthcoming global positioning system, something that we take for granted today. Okay? That was a bold decision back then. Because the beauty of it is now every satellite in the constellation all transmit at the same frequency, but they all use a different code. Yes?
That's direct sequence.
Direct sequence. Yes. Also, oh gosh, what's the numbers? When that signal gets down, it's like minus 160 dB before it hits the antenna. But due to what I described earlier as processing gain, because the spreading rate is so much faster than the data rate, that's where you get this mathematical property called processing gain. And that's why you can receive a minus 160 dB signal with a little bitty antenna, okay, on a battery device. And however, realize that data rate is 50 baud, okay? 50 bauds, very low data rate. They just kept cranking down on that baud rate until they got the processing gain, because they knew their goal was to have a handheld battery-operated receiver. So they had to keep cranking down on that data rate. That's why when a receiver, GPS receiver, has not been receiving a while and doesn't have a current almanac, it takes about 10 to 15 minutes, because at 50 baud, it takes a while to download that almanac. Okay, in 1985, the FCC made a bold decision and created the Part 15, or actually introduced spread spectrum into the Part 15 service. And the reason why is because spread spectrum has the interference resistance that we talked about and can share communications and then assign them to the ISM bands. Okay? Again, this is another bold decision by the FCC to allow spread spectrum, because in the early 70s, early 80s, spread spectrum still had this ugly connotation that it was a military system, and we don't need this ugly thing. Today we have 130 companies that have developed over more than 200 systems and products, and more than 3 million devices are now in use by consumers and businesses. And my wife even commented, I picked up the new Radio Shack catalog. I don't know how many of you have had a chance to grab it, but in the front is all their telephone products. And it's just page after page of spread spectrum telephone products. And my wife was commenting, because she knows how many years I've been doing this. She says, boy, there's a lot of spread spectrum in this Radio Shack catalog. I said, yes, dear, because it's finally catching on. It's getting into the consumer realm, and we're going to see it more and more. So it's not like it was, you know, this is not your father's spread spectrum. Yes, Ian? No, it's probably more, because the study I took this quote out of was published about 3 years ago. So it's probably it's probably double that. And it's probably double that many companies too. But everything here I've got references for. All right, what did we do on amateur radio? Well, those of you that know Paul Ronaldo, and he's not here this weekend, Paul approached AMRAD, the Amateur Radio Research and Development Organization, which is based out of Washington, D.C., to first start getting what's called a special temporary authorization from the FCC to be able to do spread spectrum on amateur radio. So this group started doing that in 1981. And then 1985, the report and order document 81 TAC 414 started the spread spectrum rules allowed in amateur radio. So it's kind of a coincidence. Part 15 spread spectrum was started in 1985. Ham radio rules for spread spectrum, allowing spread spectrum, happened in 1985. And a couple of people took that on. Glenn Elmore. Glenn was one of the original AMRAD people. Glenn is still working in amateur spread spectrum, but he started off in '89 doing his own thing with his own STA. And then Robert Buos, the same thing. I'm sorry, it's Robert that was original AMRAD. And then, of course, in 1996, we have the rulemaking 8737, which is this. It went through a comment period, and it's still pending. And this was to change the amateur rules, because right now, the amateur rules as they stand right now only limit you to 3 spreading codes and only allow you to do either frequency hop or direct sequence, but not a combination of both, which is called hybrid. So Robert Buos got a special temporary authorization to do his experimentation, and then TAPR in 1996 got a special temporary authorization. These are only good for 6 months at a time, and every 6 months we've got to give a report back and request to renew the STA. The history of AMRAD is documented in the ARRL book, the Spread Spectrum Source Book. That documents a lot of QST articles and AMRAD newsletter articles. It's not a very good book to learn about spread spectrum, because it's more of a compendium of articles, and you kind of have to pick and choose out of there to kind of, you know, get a cohesive idea of what spread spectrum is. But if you would really like to learn about the history of amateur radio and spread spectrum, that's a good book to do that. And again, the TAPR book, what we're trying to do is kind of take off where they left off. All right, we've already, I think this is kind of, everybody knows about this. Who's using it? We talked about GPS, cordless phones, wireless LANs, PRUG. I'd have put them on there. Utility readers. How many people have a gas meter man or woman come to your backyard anymore? No. The doggone thing's got a spread spectrum transmitter on it. They just drive around, and it interrogates it, and then downloads how much gas or electricity or water you used. Wireless audio speakers, wireless microphones, home security systems, medical monitoring devices, whatever you can possibly think of. All right. I've been giving this lecture now for a little over 2 years, and what are the possibilities? 2 years ago, it was really hard for me to say, gee, guys, we can do this. Well, today, you've seen it. You saw it last night. The Prug people have this actually working, and you can see the data rate. So this is not etherware, okay? It's not vaporware. Phase 3D is going to do some range experimentation using it. We've got an amateur satellite that's going to use it, and also the possibilities. How would you like to do, how would you like to blow away the EME guys that have got these great big huge arrays of Yagis, If you use spread spectrum and take advantage of processing gain, you can name that tune in 30 milliwatts, And then you can go to W5UN and just laugh him out, Tom Clark and Phil Karn wrote a very good paper about how to do spread spectrum EME using coding sequences and stuff. It was published in the 1997 Central States VHF Society Proceedings. And don't we have that? We don't have that paper up, do we?
Well, actually, I think we do. I'm not sure if we have a link to it.
We should have put that in the book. We'll get that next time. A very neat paper, very neat paper. Now this is PanSat. Well, this is a spread spectrum amateur satellite. It's going to be direct sequence. It's going to be centered at 436.5, and it's being designed and built at the Naval Postgraduate School. And the latest word I have on this, it's on the John Glenn flight going up next month. Now, everybody's going to ask me, where's the radio so we can communicate to this? Well, they're not out yet. The radio that they have for the command station is a one-of-a-kind, and they haven't got a reproducible design as of yet. But they are planning to, well, they already pretty much, if you go to their web page, you can see the specifications of their radio. So you could design to it. So everything to it, there's no secret to it. They'll tell you how you're communicating with it.
Low orbit?
Yes, it's going to be, no geosynchronous. Amateurs will never get a geosynchronous satellite. Of course, I hope my words burn in hell, but it's a very difficult thing to do. But it'll be a low Earth orbit. It'll be launched from the shuttle, so its lifetime's only going to be about 2 years.
What band?
436.5 megahertz, 70 centimeters. Microwave. Well, 436.5, that's microwave. Got it? I believe it's 1 megahertz.
Only one?
Only one. Yeah, I think the effective bit rate on the data level is 9,800 bits per second. And it's limited by our bandwidth also. And of course, the design of that got started some 5 years ago. So it was constrained by the rules we had then. Okay, so heck, I should get your machine in here, What kind of hardware is it? Well, it's going to be like a packet radio. It's going to be like a modem that you're going to put up. We would love to see spread spectrum on HF. Here's a chance to take HF and really raise the data rate and be able to reuse all of the frequencies, okay? The chipsets, there's more and more chipsets coming out. The disadvantage to many of these chipsets is they're being very specific toward cordless phones or to PCS. And for us as hams, we want to take those chipsets and bring them out and use them for our purposes So we need a much more general purpose chipset. Well, the only people that I know of that are making those are Stanford Telecom, which is what Prug is using, and also what used to be Unisys, what used to be L'Oreal, and heaven knows what it is right now. There was a company called Paramax that's been bought out a number of times. I got to do some research on it and find out where this Paramax PA100 chip is what the PanSat is using. And it's a totally programmable chip. You can make it whatever chipping rate, speed, sequence, the whole bit. Evaluation modules are out there, however, they're still very expensive. The Paramax evaluation module when I left school was $2,500. And that was down by half price of $5,000 from the earlier one. Yes, sir. Okay. Because I'm running. If you guys wanted to run to the next one, here's your next talk. Here's your chance. The SEC rules as they stand right now are very restrictive. You've got to log everything if you're doing spread spectrum. You're only allowed 3 different coding sequences. What we've done in the rulemaking is we're trying to relax and trying to deregulate so that you can go out there and experiment and not have to be constrained by the rules. And if you don't want to be constrained by the rules right now, join TAPR's STA. Okay, we're going to continue, TAPR's going to continue working hard on the rules changes. We're working hard on trying to identify some hardware we can get out to you at a price that you can afford. You're all experimenters. You all do this as a hobby. You don't do this as a day job. $500, $800, $1,000 is just a little too much to go for on that. Make your comments to the ARRL and TAPR known. You got, Dave Sumner's in there. Go tell Dave, we want spread spectrum. Further information, go to our TAPR website, find the link to spread spectrum there. And that's all I got. Any questions? Thanks. Any questions?
I have a comment.
Okay.
On the part about raising the noise floor and adding users, the duty cycle of each user isn't 100%.
That's correct.
Presumably these things don't transmit when there's no data to be transmitted.
That's correct. That's correct. So you can see a lot of issues, advantages, as you will, but believe you me, when we try to be the proponents and then you go against the ones that are not the proponents, they will use scenarios of you're constantly transmitting. The amateur power limit to spread spectrum is 100 watts. So they always use the worst case scenario on us. They say, look, you're using 100 watts, you're spreading over the whole bit, blah, blah, blah. And then they use the figures, and then they show that, hey, the frequency is totally unusable. So it's a very difficult argument because the only way to really settle that argument is get the equipment, put it on the air, and prove it.
With frequency hopping, is it possible technically to have a monitor on the band, so to speak, like a spectrum analyzer that tells you at this particular millisecond what part of the band is being used, and have that as part of the choice of where the hopping goes?
What you're describing is what's called adaptive frequency hopping, and that can be used today. And what is used today is, say, for example, a certain frequency is in use constantly. The system learns that because they know at a particular code sequence which relates to a specific frequency constantly gives them errors. So what it does is says, hey, let's just don't use it, and locks it out and continues using the other ones.
Is the TAPR version that they're working on, is it going to be adaptive?
I don't believe so. Talking with Tom, and Tom's here, you can ask him yourself. I do not believe it's adaptive.
I know it'd be more complex.
It would be. And what we want to do right now is not make it more complex, to keep the price down, and also keep the architecture open so that you can create that adaptive circuitry and add to it.
Just an observation. If we take a voice signal and we run it through a mixer and a carrier frequency to produce a narrowband, and we take the digital signal or the sequencing and run it through a mixer to produce an output, is next generation going to have one more mixer and one more signal to put in here?
If you want to have a voice frequency hop radio, is that, I'm sorry, a voice spread spectrum radio?
No, this is just wild.
Oh, okay.
Okay, right now,
Run
spread
two
spectrum
sequence?
is you got the first mixer,
Yeah.
which puts the data on, the carrier produces a
Mhm.
narrow band.
Mhm.
You have the second mixer, which injects, I'll use that term for
Another code?
another code. What happens when you take that one step further? Are we going to see that in the 21st century?
Well, the problem, you have to understand what's been the biggest problem since the 50s with spread spectrum. What is the one part of that block diagram I showed you that it causes the greatest grief and had the most research?
Probably the coding in.
The decoder, the correlation. There has been more research in correlation in spread spectrum. I can build you a spread spectrum transmitter in 2 chips. It is trivial to make a spread spectrum transmitter. You can go home and build one right now. You can go get the ARRL source book and build the one in there. Now, how are you going to get that signal and decorrelate it so that you can extract the data out of it? That has been the subject of research, and if you read the that's why it's a science unto itself, because how can we make something look noise-like but yet be repeatable and deterministic? Because noise, by definition, is not deterministic. But we can't just inject noise in here because we wouldn't be able to demodulate it. We can't just inject noise at both ends. So properties like these spreading codes being very short, okay, or very long, determine whether or not we can correlate it in a very quick amount of time or a very long amount of time. Also, the speed at which this code, what is called the chipping rate, determines how much the signal is spread. Now, what I've just described to you here is what's called a direct sequence spread spectrum signal. And if you were to take a look at that on a spectrum analyzer, this is what it looks like. You have a main lobe where the majority of the energy is contained in many side lobes. And of course it tapers off for the amount of energy that's actually there. But you would spread your signal on a center frequency, and then determined of the chipping rate and the spreading code determines how wide you're going to spread the signal. So in the case of the PRUG people that gave their presentation last night, they were limited in bandwidth. So how do they tweak that down? Do they just tweak the RF part of it down? No. They actually tweak the chipping rate down. And then that brings in the actual band limits that they were allowed to. That's why their system... Okay, let's talk about our introduction of spread spectrum. First of all, let's talk about what is spread spectrum. There's 2 major kinds of spread spectrum in use today, not to be construed as the only 2 methods of doing spread spectrum. But these 2 are pretty much washed up to the top as being the 2 that most want to implement. And that's direct sequence spread spectrum and frequency hopping spread spectrum. Let's touch a little bit on the history of spread spectrum, a little bit of history of the amateur spread spectrum, and who in the amateur communities, and of course who in the commercial community are using spread spectrum today. What are our possibilities? Why are we doing this? You know, it's spread spectrum. Let's do it just because it's spread spectrum. Actually, there's quite a bit that we can gain from it. And those of you that attended the PRUG session last night, you can see a lot of the advantages. In fact, they have it implemented, and you could see the speeds that they were able to transmit digital images. And that's all an inherent property of spread spectrum. Talk a little bit about PanSat, which is a spread spectrum amateur satellite that I'll touch on a little bit more, and of course touch on what are the hardware issues, what are our present FCC Part 97 rules that govern our spread spectrum usage, and what are our future plans in the amateur spread spectrum. And then, as I said, we'll entertain questions at the end of it, but if you have questions during the talk, please feel free to raise your hand. Okay, there will be a quiz at the end. Okay, a good instructor comes up, stomps his feet. This will be on the test, right? What is the definition of spread spectrum? And this is coming out of the Peterson, Zimmer, Borth textbook on Introduction to Spread Spectrum printed by Prentice Hall. And they have spread spectrum modulation refers to any modulation scheme that produces a spectrum for the transmitted signal much wider than the bandwidth of the information being transmitted independently from the information-bearing signal. Key word here, independently. All right, let me pick out the key words. We're going to transmit data. We're going to transmit a data stream at a certain bit per rate sequence. However, as we know, let's take 9600 baud. We got 9600 baud and we're going to use it on 2 meters. We know that's going to take up a narrow bandwidth of about 20 kilohertz. All right, that's within the definition of Part 97 rules that allows us to be able to do that. And we know that if we increase the bits per second rate, then the bandwidth widens. Now we're outside of what we're allowed to do on 2 meters. In the case of spread spectrum, what we're going to do is we're going to take that data rate and we're going to introduce a spreading signal into it and then make this signal even much wider than what the information-bearing signal needs in a narrowband sense. So the transmitted signal is much wider than the bandwidth of the information. So we got to introduce a separate code in order to get our information spreaded, and that information code is separate from the spreading code. Let's start off with something that we're familiar with. Let's talk about a narrowband system. We know in narrowband communications that we have a message that we want to send. Now this message can be either digital or analog. Then we come in here and then we mix it with an intermediate frequency so that we can basically step it up into the RF range and then be able to transmit it out. And then we're very familiar, if we were to take a look at this on an oscilloscope or a spectrum analyzer, we see that all of that information is put in a very narrow portion of the frequency spectrum, thus the name narrowband communications. Now, this of course comes across the ether in the atmosphere, and then comes across on the other side somewhat attenuated, a little bit of noise added to it. Then we demodulate it, and then we have our message come back out. Well, a spread spectrum radio uses the same components as a narrowband radio and introduces a new block in our block diagram. In this case, we saw that in a narrowband system, we had the message comes into a carrier oscillator. Here's our narrowband waveform. Everything we see from here over is familiar. We understand this part of it. Well, here's what we're doing. We take a pseudo-random number generator, or PN generator. This is a pseudo-random code, and it's a digital code, square wave. We run that into a doubly balanced mixer with our information, and then what comes out is this information spread out over several tens or several megahertz of frequency. This gets transmitted. Of course, the attenuation will be down, a little bit of narrowband noise added to it, pulse noise. Comes in, we take that same code sequence, run it through the mixer again, then what pops out is that narrowband signal. Then we run it through a demodulator and we got our message. That's it, gentlemen. That's how it's done. Now, one of the inherent capabilities of spread spectrum is its immunity to noise. Well, most noise is narrowband in nature or pulse in nature. If that is added to a spreaded signal, by virtue of despreading, the act of despreading here, those pulses basically go away. So that is why you can have noise immunity. The other one is immunity from multipath, because again, from the despreading, you take those multipath signals, they don't correlate, and they're rejected. Now, where the magic comes in is, of course, these pseudo-random generators. And there's entire mathematic books devoted to nothing but pseudo-random generators. So this block diagram right here, we could spend lectures on end just on those alone. But suffice to say that this is a code sequence that looks random. If you were to look at it on an oscilloscope, you would say, gee, that looks like noise. However, it's pseudo-random, meaning it is like noise, but it has a sequence, and it's a repeatable sequence. So